This is an explanation for EP Sheet 5, question 1.4. A sphere of radius 2 centimeters with a black surface is cooled and then suspended in a large evacuated enclosure, the black walls of which are maintained at 27 degrees Celsius. If the rate of change of thermal energy of the sphere is 1.85 joules per second, when its temperature is negative 73 degrees Celsius, calculate the value for the Stefan constant. So the things I want you to think about when trying to solve this question is how much heat is gained by the walls, how much heat is lost by the walls, how much thermal energy is lost by the ball, how much thermal energy is gained by the ball. So if you look at what I've written down here, they seem like different things, but they're actually all the same thing. Heat and thermal energy are the same thing. And think about the walls. If you say a certain amount of heat is lost or gained, realistically that could be the same thing. A negative gain is a loss, and a negative loss is a gain. And the same goes for the ball. So try and think about that as you proceed through the question. All heat energy lost by the walls is gained by the ball. All heat lost by the ball is gained by the walls. But the walls are maintained at its current temperature, so we don't actually see a change in temperature for the walls. Either way, we haven't been asked to calculate a change in temperature. Just like we've been asked to calculate a rate of heat flow or heat exchange or heat loss. So the rate of heat flow is determined using the equation Q, the thermal energy. Well, it's meant to be Q dot. So rate of thermal energy is equal to sigma, which is Stefan's constant, multiplied by the area of the object in question, multiplied by the change in temperature. This isn't actually a change in temperature. We have delta T here, but it's more of a difference in temperature. So we've expanded on that below. So we've got delta T to the power 4 is equal to the wall temperature to the 4th power, subtract the sphere temperature to the 4th power. So below that we can see sigma multiplied by A of the sphere multiplied by 200 to the power of 4 is the heat radiated by the sphere. And below that we've got a similar equation, and this is the heat radiated by the walls. So if you think about the sphere, it's going to radiate some energy, but then it's going to receive some energy from the walls, and that difference is how we determine the rate of heat flow. So below that we've got the combined equation, which takes into account both the temperatures, and you can see now we could have a value for Q. We've been told to calculate Stefan's constant, so we're going to pretend we don't know what that is right now. But just to expand on that a bit further, if we were to use 300 to the power 4, subtract 200 to the power 4, we'd get a positive value for Q. If we had to swap around, we'd get a negative value. The sign of the result doesn't really matter, but the magnitude matters. The main thing is with these questions, you have to understand that if something is hotter and something is cooler, the hotter one will radiate energy. Well, it'll have a net energy loss, while the cooler object will have a net energy gain. So in this case, our sphere is being heated, so it will have a negative net heat flow. So towards the bottom here, we could say that our equation of the rate of heat flow is equal to Stefan's constant multiplied by A, multiplied by the change in temperature to the 4th power, and tells us the rate of heat energy flow out of the first object and then to the second. Our answer is negative because the sphere is being warmed and the heat energy is flowing out of the walls. For this last slide, we're going to just work towards the solution. So we have our rate of heat energy flow. It's 1.85 joules per second, which is the same as 1.85 watts. And we can equate that to the equation we used earlier and say A is the area of our sphere. So the area of a sphere is the same as the area of a circle with the same radius, but you multiply that by 4. So we've got 4 pi r squared, and we can rearrange our equation to find sigma, and well, yeah, you can see it's been done here on the slide. So we end up with a value of 5.66 times 10 to the minus 8 watts per meter squared, Kelvin to the power of 4.